Good morning, everybody. My name is JeanHeyd Meneide. I am a student who is currently working towards getting his undergraduate degree. My nickname online, or I guess the handle I'm most known for, is the PhD, but it's still a work in progress to actually being a PhD. So I just consider it a stood promise on my stood future. But what I'm here to talk to all of you about is Unicode. Specifically, I've been working on a library for a little while, and I gave a talk about Unicode at CppCon a couple months ago. This talk is going to be building a little bit on that, but don't worry if this is, even though this says part 2 of 5, this is a talk there I will kind of recap some of what happened before, so you don't feel lost as we go through this one. But I will be going into some of the lower level details. So to kind of go through and recap, I guess, on what the work I've been doing and CS+ in general as far as Unicode is concerned. These are the things that Unicode, or that CS+ supports as far as Unicode is concerned. Nothing. There's really not much Unicode support in CS+ at all. The one utility we had for even converting strings we had to yank out because it was really bad. It was called wstringconvert. And most of the other locales and facets and other things don't really handle multi-byte encodings or other things like that very well. So yeah, Unicode support is not a great story in C++. One of the other things that's been really bad is that char. Char is absolutely not your friend in the C++ world. To give you an example, this is C++ kind of 17 code, right? I have a U8 string literal with a character, and then I also have another stood string using a regular string literal. Then I say, and I'm kind of like in the name, kind of like totally asserting that these are both like UTF-8 strings, right? And so I assert that they're equal, right? And you would think that they're equal, except they're not. Put this on a Windows platform, that'll fail. You go to a Linux platform where somebody sets the Lang environment variable to something different, this will fail, and all a bunch of other kinds of crazy things that make sure that this code fails, even though visually it looks the same, and even if you're on your editor it looks the same and everything supposedly looks like it's supposed to be right, it won't be. So very easy pitfalls to walk yourself into when you're dealing with char, when you're dealing with stood string and everything kind of char based in the standard library. Char continues to not be your friend, especially when you're 40,000 lines, 40,000 lines to your code base. You got a function, it's called process. It takes a stood string, and you pass it a bunch of string literals or just stuff that comes from the command line or just other things that come in other places. And when you're inside this function process, you have no idea what it's been called with or whether or not the data actually is supposed to be UTF-8. And this presents a real problem because it makes it impossible to differentiate even at compile time from different literals. So even if you have a U8 literal, it still gets passed in as char, and your process still says it's totally UTF-8. But when you start passing other things, and the encoding is different, and any processing that you had that was dependent on the fact that you had UTF-8 or anything like that kind of goes out the window, and you end up with very much corrupt state in your program. Thankfully, this was somewhat fixed for CS+20. They introduced a char8t type. So every time you do U8 and put a string literal there, you actually get UTF-8, well-formed UTF-8 across all compilers. It's wonderful. The other benefit is that U8 and that char8t and U8 provides is that you have essentially strong type defs now. So before, when you did kind of disgusting things with just stood string, it was impossible to tell the difference between these two literals, right? And they both kind of compiled just fine and went into the stood string. But in CS+20, this doesn't happen anymore, right? So this line doesn't even compile anymore because it's trying to compare a stood U8 string to a stood string, and that just doesn't work. And so, believe it or not, this actually really helps with your programs. It's weird, like compile errors. Why would I want more compile errors in my program? But this actually really helps because it allows you to assert in the type system that what you're getting and what you're working with is UTF-8, which means that if you, say, put this in the core of your program and you started working with it and you started working outwards from there squashing all the compiler errors and adding explicit conversions, like say adding an encode function that goes from also totally UTF-8 to actually totally UTF-8. You can kind of push out the places where you accidentally use system encoding or accidentally use string literals of the wrong type, and ensure that you're always using UTF-8 all the time. The way you do this before CS+20 is that you use unsigned char. This is kind of a hack that not only me, but a lot of other people have been using in pre-CS+20 times to basically assert that the work that we're doing and the strings that we're using are UTF-8. And what this allows us to do is that we would place our version of a U8 string inside inside the core of our program, and then every time we found compiler errors, we either had to check to make sure that we were doing an explicit conversion if it came from the system encoding, or we realized that it is definitely UTF-8, and so we change that to UTF-8, and we kind of propagate this out to the edges of our program until we basically only end up in places where we were dealing with command line args or like network buffers or like inter-process communication, things like that, where that's the only time where we actually had stood strings and we made sure that we explicitly converted. And so this is a quick kind of easy way to let the compiler help you track down all the places where you could possibly be implicitly converting and making mistakes. So one of the other things I guess I covered in my first talk was how busted the C standard was. There's this lovely table here, and as you can see, there's a lot of red X's. And what all these red X's mean is that C does not have a conversion function to go from what's in the column to what's in the row, or what's in the row to what's in the column. It's bidirectional. And this is a real problem. You didn't really have any good way, or at least any performant way, to go from, say, the multi-byte encoding, which is what the char star is associated with in the standard library, and what the locale associates it with, to a statically known encoding like UTF-16 or UTF-32 or even UTF-8. And this presented a lot of problems. This also presented some performance pitfalls because the only versions of the encoding functions they gave you were the single character at a time conversion functions, which are detrimentally slow for anyone's real application. A lot of these function calls are hidden behind DLLs or put in system DLLs. So doing a DLL call just to convert 2 bytes at a time when you have 1 million bytes to process is not a good way of working with stuff. So this was a pretty big problem, and so I actually wrote a paper to fix it, and I did. So there was a meeting of the C Standards Committee at Ithaca, New York, and I presented a paper to basically propose all the things that you see the P's next to. And they actually pretty much nearly unanimously voted to fix it. I think the vote was like 14-0-2, which is 14-4, 0 against, and 2 abstain. So this actually might end up in a version of the C standard relatively soon. They have a different cadence than C++. They kind of work on like a 6, 7, 8-ish year time frame, and C++ is definitely on the 3-year time frame. But they did agree that they want this problem fixed. So this will be good for not only providing a C++ API, but a C API as well that can be used by everybody. The other thing that they approved was sized functions as well. So for a lot of these functions, it was very, very difficult to work with them because they always stopped at the first null terminator, basically, right? So if you wanted to work with any data that had embedded nulls, well, good luck, right? So I was able to propose, and they accepted the direction to have end style of these C functions as well. So you can pass in a size, and it'll go up until the size rather than up until the first null terminator. And the good thing of this is that not only does it allow embedded nulls, but it also allows SIMD to be used even on more exotic architectures. So if you happen to work with most CPUs today, if you use SIMD and you happen to accidentally overrun the buffer, most of those SIMD instructions won't do crazy things to your machine. But there are some exotic architectures that if you use SIMD and you were to, say, spill over the edge of your array and start going past the null terminator, you'd kind of tank your processor there. So in this case, right, by having the size and knowing the size in advance, you can safely chunk out the work to an SIMD processor, whether it's AVX512 instructions or just your basic SC2. But having these size functions really will enable us to get the maximum amount of performance out of the C interface. A small sidebar. There are sized kind of functions in the C standard. They're in Annex K. They're the R-size functions. They're the conversion, it's the name of the function underscore R. And what those are basically the security versions, or the secure versions of the conversion functions that are already in the C standard. And you'd think that it would be great, right? That with these R-size functions, even if it's in Annex, right, there's a bunch of people who still implement those, and the idea here would be that, you know, people would be able to have both safety with this new R-size max thing, which basically help prevent errors when you happen to have a negative number from some math and you pass it into the function and it became unsigned. And so they defined this R max thing to basically be the unsigned max divided by 2, so that that would be the maximum limit you could pass in, and so it would catch if you happen to overflow over that into an unsigned number. And of course they said implementation will do the right thing, R size will be great, it's going to be awesome, and so they put it in Annex K, they shipped it, and they made some serious mistakes with it, actually. It turns out that while the normative encouragement was sort of like, hey, you should use R size, you should use size max divided by 2 as the defined for your R size, for your R size max, it turns out that's not what a lot of implementations did. So instead of having, say, 2 billion bytes of space that you could work with, what actually ended up happening is instead you had implementations defining R size max to be something really, really small. And so what happened is that you would call this R size function thinking that you were doing the safe and right thing, and then it would be greater than R size max, and the function would return an error, right? But you normally programming on like your desktop machine or whatever, like in Visual, like on Microsoft with Visual Studio or on your typical Linux distribution, right? R size max is definitely like 2 billion, right? It's the, you know, the 32-bit or the 64-bit limit. But when you say port it to some exotic platform and you try to use these functions, they'd have limits as low as, you know, the maximum of a 16-bit integer, and so that really tanked not only cross-platform ability but also performance. And so, as a small sidebar, there is always a Destination 9000. There's always an implementation that will do the maximally horrible thing to you and your code. And in a small corollary, there's always a hell++, right? There's always a C++ implementation that will also do the horrible, terrible thing. And it always exists. No matter how safe you think you are, somebody somewhere is going to implement a platform that makes even the standard library not very useful as a standard. But the good news is that the C standard is still making progress, right? So they accepted my paper, and we're working on other things. But WG14, the C standard, has kind of a general rule in that there should at least be 2 implementations of a thing. And they also want you to build on existing practice. So I'm working with Philip K. Krauss, who works on the small device C compiler. Now, he's already got an implementation of some of these functions in SDCC. But I'm working on a freestanding implementation in a library called Unicode, which is basically just C Unicode, but I kind of named it cool because why not? And hopefully I'll be able to finish that and also push this into the musil-C library and the glibc library. So that's a lot of C stuff. But now we want to get to kind of the C++ stuff that, you know, I really spend a lot of my time on, that I've really been working on. As you see, this is, I guess, an image from the last talk I gave, you know, talking about the baseline Unicode support I want for C++23. And so we're going to kind of go into a little bit more of that and explain some of those details. So the biggest part of this is the encoding concept. And the idea is that there is that there needs to be a core abstraction here that represents encoding and decoding. And it has a couple of member functions and type defs and static member variables that tell you a little bit about it. And so I'm not just going to throw the concept at you, I'm going to illustrate it instead. So here's some helper types, right? So I've got this empty struct. I've got a couple type defs that are kind of self-explanatory, right? They're spans of byte or car8t or car16t or car32t. And I've got this encoding error C, which kind of defines, you know, just some encoding errors that I'll be using, you know, throughout the presentation. Some other helper types is this decode result and encode result types. And so what these are is results that you get back from calling a low-level encode or decode operation. And we'll get into what all of these mean, but basically it contains your error code, whether or not you handled the error. It has a reference to the state struct, which I'll explain in a moment, and then it has the input and output, which, depending on whether you're encoding or decoding, is either UTF-32 to UTF-8 or UTF-8 to UTF-32. And we'll explain a little bit more about as we go along. Also, the other thing that we're going to talk about is the error callbacks. So in this case, we're using this kind of, it's not quite in the standard yet. It's supposed to be in for CS+23. It was supposed to go in CS+20, but it didn't quite make it. Vittorio Romeo has a bunch of talks on it. Stood function ref. This is kind of like the lightweight, nice, neat version of stood function, so that's kind of why I'm showing it here. But you could easily lop off the underscore ref and just say stood function, and it would work just fine too. So these are functions which either return an encode result or decode result and take an encode result and decode result. They also take the current encoding, and they also take a view into the number of code units or code points that have already been written. And again, this seems a little bit dense, but I'll kind of illustrate this in a second. So encoding objects, right? We need something that tells us how we're going to go from some encoded blob of stuff to stuff that we can understand. In this case, right, we say want to work with UTF-8, so we can take a bunch of code units that are char8t and get a bunch of code points that we can perform Unicode algorithms on and everything else. And so the idea behind this is that you define a bunch of three necessary type defs, which is the code unit, which is the unit that the encoding works in, the code point, which is the single indivisible unit of information that can be output without, like causing problems. State, which represents the state that the encoding needs to do between every single call. In the case of UTF-8, there is no state that's needed between serializing each chunk of UTF-8, so we just have an empty struct here. Then we define two other constant variables. So we have max code points, which is the number of code points, the maximum number of code points that can be pushed out by any given decode operation, and max code units, which is the maximum number of bytes or units that can be pushed out by any single encode operation. And then, of course, you just define the two functions using all of this. So there's encode 1 and there's decode 1, which, as the name implies, right, it either encodes a single unit of information or decodes a single unit of information. Right? Is everybody? We're all on the same page. Great, wonderful. Feel free to pipe up with questions and stuff if you need to. And so this is kind of this is the same thing, just with UTF-16. So you can see the code unit changed from char8t to char16t. The max code unit changed from being 4 to 2 now, because that's the maximum number of code units that you can slog through to get to a single code point. And then, of course, we have the encode 1 and decode 1 here, but we're just changed the input types and the output types for the encode and the decode to be U16 spans rather than U32 spans, right? Does that all? Very simple, right? Like you just change a couple things and you get like a UTF-16 decoder, right? At least the interface for one, right? Does that make sense? Great. Awesome. And there's also other kinds of encoding objects that you can have, right? So in this case, this is the GB18030 encoding, which is the required encoding in the PRC in China. And so in this case, our code unit is a stood byte because it's a byte-based encoding. And we're using a different kind of code point rather than just the char32t. In this case, the maximum number of code points that can be put out is 1, and the max code units is 2. And so as you can see, our output type is the span of code points, and the input for the decode is span of code points. So very simple, right? Does everybody kind of see how this is changing and it all makes sense? All links together? Yeah, more or less? Okay. But one of the things I did there is I changed the code point type, right? So usually when you're decoding, right, when you're decoding or when you're encoding from stuff, you want to decode to char32t, which is your typical Unicode code point, or encode from that to the storage type you need. The thing about GB18030 is that's actually already a Unicode transformation format that's again mandated by the People's Republic of China, but it has slightly different semantics. It uses a bunch of private use area characters to communicate outside information. And so the idea here is that if we were to make this be, if we were to use char32t here, it's less of an indication that this is actually has a different kind of code point and that it might be using private use area characters or other special characters inside of the Unicode repertoire, right? So the idea here is that by showing a code point, by having a different code point type, you can statically signal to both the user and to the people who are writing this that it has different semantics, right? That you might be using private use area characters, that you might be using other things like that. And so that's the reason why we changed the code point. In fact, one of the precursors to this library, Tom Honerman's text view, spent a lot of time actually trying to define strong code point types for not just for things like GB 108030, but for every single encoding, like UTF-8 1632, you would have a UTF-32 code point type and things like that. And he explored this idea of making like a strong set of characters and a strong code point type for every single encoding, but the feedback that we got from implementers and from people who work with this kind of stuff, like the Mozilla Foundation, from people who work on Google, people who work on ICU, is that they actually don't necessarily like having a strong type def for everything. They definitely want to use like char8t or sometimes even just plain uint32t to do a lot of their transcoding work. So right now we have a design that allows for it, that we allow you to have a strong type def, but we kind of strongly encourage that you use kind of char32 most of the time anyway. And the reason for that is that there's a lot of layers above what I'm going to be talking about today that will kind of assume that char32t is a Unicode code point. And if you don't have something that can work with char32t or that has the same operations as char32t, those algorithms will kind of fall on their face because they won't know how to work with stuff. The good news is that you can kind of prevent some of those consequences and prevent the higher levels from not working by just having an implicit conversion or an implicit constructor that allows you to create a code point for these kinds of things. All right, does that make some kind of high level sense? Yeah. Yes.
Just to clarify, if I want to use this encoding to convert between, let's say, UTF-16 and I don't know how to pronounce that encoding.
Yeah.
Then there are conversion operations in GB code point from char32 and to char32, or not? Does it have to be one-to-one mapping between these code points and char32 code points?
It doesn't necessarily have to be a one-to-one mapping. And I cover that, I guess, in my first talk, in that there's allowed to be lossy conversions and there's allowed to be things like that, but you have to be explicit about it. And I might go into that a little bit later, but you don't have to provide a direct mapping between this encoding and like UTF-16 or something like that. What we do is we round trip through a common intermediary, which generally is char32t. And again, because we have this conversion operator, it works fine, right? Does that make sense?
All right, thank you.
Yeah. So yeah, one of the things is whether or not is char32t like as the code point type enough, and is it plausible that we need to handle different strong code point types in higher levels of the code? And do we want to have better character sets like strong encoding and a character collection association kind of made? These are actually open questions. I don't quite have the full answer to them. As my implementation has kind of formed out, I've kind of been feeling out that char32t is definitely enough as the Unicode code point type, but I think there is still some merit in being able to define your own code point type for cases like these where you want to communicate extra semantics to the user. So that's that. And of course, you get a kind of a slew of standard encodings, right? So we give you ASCII, narrow execution, which is the locale-based encoding, wide execution, which is the wide character locale-based encoding, which you wouldn't think would be based off of a locale, because usually wchar-t, which is the wide execution, is generally associated with either UTF-16 or UTF-32 on almost all platforms, except if you happen to find yourself on an IBM machine, and that IBM machine is in either China or Japan or Taiwan, and you'll end up with an encoding that is neither UTF-16 nor UTF-32. And so the whole thing will actually break down if you were assuming that WCAR-T was actually going to be one of those two, which is painful because I was under the blissful, magical assumption that WCAR-T was at least mildly safe for that kind of thing, but nope, it's not. So these are the 5 kind of like base stock encodings you get, and of course we also have these basic UTF, basic UTF-8, basic UTF-16, basic UTF-32. And the reasons we have these encodings, or these templated encodings, is because there are many code bases where people have already kind of settled on a certain kind of character type for their UTF-8, 16, or 32. So some people have settled on UINT-16. Some people have settled on char. I don't recommend doing any of those things. I recommend that, of course, you use char8T, char16, char32T, but legacy code has different needs, and so we support them by giving them an escape hatch with this basic UTF-8 stuff. But everybody else who's kind of just getting started or who has the time to port can kind of use these nicer type defs, these short, nice type defs here. Okay, so that's kind of a general quick run-through of the encoding objects. And what we're now going to start talking about is some of the more gritty details of the text coding library that I've been working on lately. And so one of the, actually it turns out surprisingly interesting and somewhat difficult encodings to get right is this any encoding, right? So it's a pretty common thing to want to work with encodings that are only known at runtime, right? Whether it comes in through an HTML as meta char set, whether it's a byte order mark, whether you have a document processing and they tell you at this point you're dealing with this encoding and at this point you're dealing with that encoding, or just basic data exchange formats, right, where you don't know the data a priori, right? So we need some way of being able to work with encodings that don't necessarily, that aren't necessarily fixed in time, that aren't fixed at compile time. And so what we do is we actually just define another encoding object, right? But we do some subtle differences here. What we do here is we have a code unit that's stood byte, and the reason we want a code unit of stood byte is because anything can be turned into a chunk of bytes, right? So whether it's an input of UTF-16 or an input of UTF-32 or GB18030, it can always be turned into bytes, right? So this serves as a good like foundational layer for like having an any encoding type. We want the code point type to be char32T because that's ultimately the only kind of thing we really want to support in our any encoding. There's the final version of this will probably be a little bit more templated and allow you to change a couple things about this, but for the most part, this is how any encoding will work. We define some kind of safe values for max code points and max code units. Basically, values large enough that it will be able to handle anything that comes in or out. And we also have a constructor here that just kind of takes any previous encoding object and then kind of like does the magic that kind of type erases that encoding and stores it in some magic, storage behind. And then of course we have the encode1 and decode1 functions. And in this case we have the byte span being the input and the byte span being the output for the decode operation. Does that all make sense for everybody? Great. Right, so as you can see, right, this is just like another encoding object, right? Like you don't have to go out of your way to define a new thing, right? You can just write another encoding object and take care of some of the details yourself, and it still plugs into the system and still works, right? Okay. So any encoding, right, is supposed to be just like value type wrapper around polymorphic storage, right? So it's sort of similar to stood function or the upcoming unique function that I think was renamed to any invocable, or things of basically of that nature. And internally, we do a little bit of small size optimization because we know that most encodings are stateless and tiny and have no size, and so we can just store it really cleanly and don't have to do any. We don't have to force any virtual lookup. But remember those wide execution encodings I mentioned before? These ones are actually stateful because the state that they work on is a stood MB state T. This is like defined by the standard, right? Whenever you use any of the C conversion functions or some of the locale stuff in C++, you have to pass around and work with a stood MB state T. And so the actual state for this, whether it's the wide state or the narrow state, for the wide WCAR-T execution encoding or the char-based execution encoding that's based on locale, you have this kind of state type that has a stood MB state T inside of it. And this presented a little bit of a problem with the library design, right? when I was writing like higher level functions like decode, encode, and transcode that would do like bulk conversions to this and that, I had this freedom in the previous in older versions of this where when I had UTF-8, 60, and 32 and they all had their own state type defs and everything was statically defined, right, I could just make the assumption that I could get the encoding state of some encoding and then just spin it up, right? It was just like a regular small type. I could just default construct it and I have a fresh state to work on. Or if I had some old state and I needed to reset it, right, I could just make a new state and then copy construct it or move construct it back to the over the old state, right? And that's how I would reset the state so I can keep doing computations on it, right? This becomes a problem because with any encoding, right, what is the state, right? Like, so I have this. I have this constructor, right, that is templated, it takes an encoding, and after I take that encoding, I end up in the situation where I do all the type erasure, right, I create the backend that, you'll call for encode 1 and decode 1 and all of that, but then, like, what's the state type, right? Like, I type erase the encoding, and I have this a way of working with things where I can just assume I can get the state and reset it and do all this other stuff, but if it's type erased, how can I guarantee that I can do that, right? And so default construction especially becomes a really big problem because how do I default construct a state for something that's been type erased and I don't know what it is, right? Like all that information is gone. So this was really a problem for me. And it took a lot of thinking and a lot of like different tries. First I had an any state idea, right? But the problem is that constructor needs more information than I have on hand, right? I need to also give any state the encoding that I'm working with, right? Not the any encoding, but the actual base encoding that's inside of it, right? So now I'm in a bit of a conundrum, right? So how do I do this, right? Any state needs information from the type erase any encoding. It needs to get to the guts of any encoding, right? But do I want to keep a default constructor, right? How do I make that work without violating the fact that I don't have that information, right? Also, how do I do things like copies, right? Like, do I write like a type erase wrapper that has like a clone method that like returns a pointer, and then like I do a bunch of like unique pointer shenanigans underneath, before, like when I had UTF-8, 16, 32, right? These were all like stateless encodings, and it was all nice and wonderful, right? And even for the stateful encodings, right, it was still statically known, so I could just create the thing and then destroy the thing, right? It was very simple. But now I'm talking about maybe I need to like whip up a new unique pointer every time I do something, right? That's very expensive, especially if I'm doing a repeated decode or encode operation, right? So I came across all these like really these problems, right? So I started trying to think of solutions, right? One idea was to fuse the encoding object and the state together, right? So take the encoding object, take the state, and smash them together to basically have everything all in one class, right? Or all in one object. The problem is that it doesn't really help with the default constructor problem, right? Like, how do I clear the state, or how do I create a fresh state? There's no way to have a default constructor on any encoding because, again, I need to pass in the encoding so it can type erase it. And the other bad thing about that is that if I did make a default constructor on any encoding, right, it would have to behave sort of like std function, where if you default construct the thing, it like says, oh, I'm a std function, but I have nothing inside of me, right? And then every time you try to call it, then it's empty, right? It throws an exception, and you're like, why is that thing there? And so you get like null pointer-ish semantics on std function, and I really don't want null pointer-ish semantics on any encoding because that's more things that the user has to think about. It complicates the design space for the user. So maybe what I should do is that I should just like specifically like hard code the fact that any encoding exists and just like check for it on all my algorithms, right? Like, am I working with any encoding? Okay, I can't just like freshly create the state. I have to do some like special member function calls on it or whatever, right? But the problem with that is that's no longer generic, and it's kind of patchy the way std reference wrapper is patchy in the std lib, right? Like, so for example, if you can use a function called std invoke, right? And what that does is that it, in the standard library, what it does is it basically lets you to treat something like it's a general callable thing, right? And it abstracts away all the fact that things are pointed to member function or that it's a lambda or whatever else. And in-std invoke it has very specific wording in the standard lib to say, by the way, if you pass me a std reference wrapper, I will unwrap it for you and do the right thing, right? I'll get the reference out of it and do the right thing. But this doesn't work for, say, if I write my own reference wrapper, or if I write my own thick reference where I put a pointer to a vector and an integer, right, to like index into the vector, and that's how I get my reference, right? That won't work with std invoker or the standard library because it's only specifically for std reference wrapper, right? So I don't want to end up in a place where I'm like making secret black doors or implementers only like special club stuff, because that means that the user can't opt into it, right? And if you wanted to write your own type erased encoding, or you wanted to write your own, say, encoding that didn't use type erasure at all, but instead used std variant, right? Like, there's all these cases where if I start specifically encoding for any encoding, I'll end up in a situation where it's very bad for everybody. So that didn't work out, and so I decided maybe I should like store the state on the encoding object somehow, but then still keep it like separate some way, and find a way to get the data at runtime, be able to detect the fact that there's like this self-storage of the thing on the encoding at compile time, and maybe have this self-referential encoding object where like the state points to itself, right? And that was like kind of like a weird idea, and I thought about it like self-referential, like, self-referential encoding. I could have it point to itself, and that's exactly what I did, actually. So I set the state to be exactly the class itself. And this is wonky. This is really wonky and kind of weird. But the good thing about this is that it basically allowed me to provide a generic way to say that, listen, if you have a state type that points to the encoding itself, then the encoding itself is the state, right? So this gives people freedom to keep the stateless versions of the UTF-8 1632, keep it slim, keep it with no overhead, but on specific encodings where they care, especially in the case of like any encoding, or if you had a special invariant encoding, you can set the state using this kind of idiom, and in that way, it allows me as a programmer in my library to properly do the right thing and treat your encoding and your state with the provisions it needs. And the great thing is, of course, it's super easy to check for, right? I just have to do if const expr, is this the same, is the encoding the same as the encoding state? Then I know that you have, a special encoding that needs to be given information from the encoding in order to make the state work, right? And that's great, right? So there's no special secret provision. Users can make their own version of this. I'm not writing special backdoors into the library, right? And everything kind of just propagates nicely, right? But there still is a bit of a question of like how someone has to clear the state, right? So it's still kind of type erased, and I still need to be able to say a way like, listen, I'm restarting this encoding operation. I need to clear the state. So in that case, we might need to have like a utility-free function that I use internally called reset state. I'm not sure if I don't think the user will have to see it too much, but if they get into the business of writing a lot of encoding objects, they might have to. But the good idea here is that there's no special provision, secret provision here. But I think the only bad part of this is that it's introducing an additional layer of complexity to the API. Like having the self-referential state, encoding object is a little bit. It's not necessarily novel. It's just a little bit kind of weird to think about. But it's. I think so far it's the best way I've been able to come up with handling it with minimal overhead and everything else. Does that kind of all pan out? Make sense about how I? Awesome. So that's about it, I guess, for any encoding. And so one of the things I also want to kind of talk about as far as like the details of the API is error handlers. Normally, most libraries in the standard, most std-lib libraries kind of make the decision about error handling for you. Whether they provide you a dual API like std file system, or they just say we're using exceptions and you just have to deal with it. They kind of decide up front how you're going to be able to handle certain classes of errors. And while that's nice, it's also fairly detrimental in that it makes it so that there's a large swath of people who can't use that kind of code or have to use special flags to opt in and out. And so when I set out to design std text, I had a very early goal that this would be viable on the very small machines and very tiny machines, right? Which means I need to give the user a first-class way of avoiding exceptions and avoiding other machinery that would cause them to throw the whole thing out the window and design their own, right? Because again, this is something that I want to put in the standard library. So this is where error handlers come in. And it's not really a terribly new concept. These are the type defs from before, with the U8 span and the decode result, encode result, and the UTF-8 encoding. And what you can see here is it's just a callback, right? Like I'm just defining a std function or std function ref in this case that gets called anytime an error happens, right? And so this isn't necessarily all that big of a deal. It's not really like revolutionary. I didn't come up with like the best new thing since like static exceptions or something. It's just a callback. But that callback turns out to have very, very powerful implications for the whole API. So to kind of dig into this, right, I'm going to name these parameters so I can kind of explain it, right? If you were to write an error handler, right, for a decode operation, you would the things you would get passed by the encoding when an error occurs is the encoding that you're working with, right? The current state that you're reading from, right, which is the current result value that the encoding is working on, and a view, a span or something similar of what has been consumed so far by the encoding object as it's done its work. And the reason we have all of this information here, because it's a lot, the reason we have all this information here is so that someone can kind of have all the different ways of recovering from an error. And I'm going to kind of show a little bit of that in a moment. But at a high level, what this does is it helps preserve algorithmic information, right? So it hands you the current encoding, right? And in the case of any encoding, that's extremely useful because I need to be able to query things like what actually is the encoding inside of this thing, right? And is there any state information I should be caring about, right? The other part about this is if I get the intended result type, on that result type come the input and output parameters that I showed you before from that struct, and that comes very in handy because it means I can arbitrarily manipulate the input and output parameters that are going to carry the data back to the user, which is very helpful in quite a few cases. And the last part is that there's no read to write like caching iterators. So when Tom Honerman implemented text view, he had a need that he sometimes needed to go back and read like old things that he pulled out of input iterators. The problem with input iterators is that once you read from it, there's no guarantee that you can keep reading and get the same value again, right? Once you read from it, like the thing moves on, and you're left with something that you're left with. You lose data if you don't remember to save it or cache it. And so by having this third parameter, this U8 span consumed so far, what this means is it gives you the number of char8ts that have already been read and hands that to you to make sure that you don't lose it. And that's useful, again, for either perhaps saving that if you're, say, reading from a network or reading from a stream that you can't quite write back into. You can save that stuff for later and use it to chain to the next encoding call, right? So that you save those bytes and then you call the next encoding operation with those bytes so that it continues properly, right? Rather than being lost and having to get mangled data. So these are some of the high-level algorithmic properties. But one of the things I really want to talk about is that result thing by value. So this as a reminder, these are the structs, right? We have the inputs and the outputs, the state, the error code, and whether or not we handled the error. The really important thing about this is that when we give the input and output that are passed to the encodings through to the user, through this result type, it allows them to do arbitrarily complex or arbitrarily simple computations to report their errors. So I'll give you a quick example here. I'm writing an error handler, right? And it gets called, right? And it's for UTF-8. So I have a decode operation. It's failing, so it calls my error handler. I get the encoding, the UTF-8, which I don't care about, so I don't give it a name. I get the decode result, which I do care about, so I do give it a name. And then there's the U8 span that I don't care about because I'm not really interested in like caching iterators or anything else. In my code here, what I'm doing is, well, first I get a reference to the input, right? Just so I can have shorter names on my slides. But I have the result.input, right? And so what I do here is I do a find if to find the first byte in my span of inputs that is actually a valid start byte, right? UTF-8 has this nice property that every single byte that's meant to be a start byte has a very specific code sequence, right? So I can check for that, right? And so rather than getting an error, right, and then just immediately inserting a replacement character and then returning, instead what I can do is I can skip all the bad bytes, all the incomplete sequence bytes, or all the bad sequence bytes, get to a valid starting byte, set that back into my result.input. I'm assigning it in through inref, and then now that I've done that, I've successfully discarded all of the characters that would have generated more errors, right? Because I would go back into the decode loop, I start trying to decode stuff, and I get another bad byte, and then I would go out and do it again. I could do this up to as many as 4 times for 4 bad input sequences until I maybe get to a valid start byte, right? And so by having this and by having this result type, I can skip all the bad characters, and this is incredibly useful because. Believe it or not, there's implementations where whether you actually serialize 1 replacement character or 4 replacement characters for a bad sequence matters. In fact, this is actually a sticking point for a lot of the implementers of web browsers. ICU at one point kind of arbitrarily decided, it's probably nicer if we change the way that we handled how we output replacement characters. And they made that change in I think it was like Unicode 8, Unicode version 8, something like that. And that caused breakages in web browsers because they couldn't agree on the number of replacement characters and everything else that they were supposed to be communicating across the wire. So libraries were not performing correctly and doing the wrong thing. Henry Savonen, who works for Mozilla and who represented them to the web standards body for a while, actually had a very long blog post about this. But basically, the idea behind these error handlers is that there's a lot of different behaviors that people want and expect out of what they want their decoding to do, or what they want their encoding or decoding to do when they encounter an error. And so by providing them all this information, they get to do all that arbitrary computation. They get to decide whether they want to throw. They can decide whether they want to just ignore all the errors and return. They can decide whether they want to maybe handle certain different cases. In fact, these are the ones actually that we plan to provide with the standard, is that you get a throw handler, which is, every time an error happens, you throw. This is not the default because there's too much ill-formed text in the world, and you'd end up in a case where you'd actually DDoS yourself and your services if that was the default, right? Because you decode something, it'd be wrong, especially if you're working on Windows. You'd open an editor and then it would just explode because it defaults to the throw handler, right? And that's not what we want here. There's a replacement handler, which what it does is it attempts to replace a character FFFD, the typical, it's usually the black diamond box of the replacement character that you usually see. But in the case that it can't handle that, we have some additional logic in there to do things like if it can't handle that, when we try the ASCII question mark, see if that can encode incorrectly, and a bunch of other stuff as well. We also have an ignore incomplete handler, which is very handy because what it does is it ignores the error called incomplete sequence. And you get that error when you're processing a number of bytes, but you reach the end of the input sequence, but there's nothing wrong so far. It's just that you don't have any more input, right? Now, normally that would be an error because, well, there's nothing more to process. I can't give you a complete code unit. But if you're, say, on the network, right, and you're streaming data, you don't want to have that actually result in a real hard error. So we have this ignore incomplete handler, which just magically massages away the incomplete sequence error code and lets you recover the data and hold on to it. And of course, as I mentioned before, we have a default error handler here, a replacement error handler, because we really, really, really want to avoid a case where we DDoS users because they just they use the throw error handler. You, of course, can substitute in the throw handler when you're doing your regular debug development, right? So you get instant errors, right when something bad happens. But for general development, and even recommended by the Unicode Consortium, you definitely want the replacement error handler, right? Does that make sense, everybody? Yeah. Okay. So that's about it. That's those some final thoughts. Type erasure is very hard when you have 2 separate pieces. And finding an even more elegant solution for any encoding. I think the one I have right now is decent. It's a little weird, but it's decent. Would probably improve the API a little bit. And retaining the flexibility at these lower levels of the API is very, very, very helpful. It definitely allows users to do novel things or interesting things, or to maintain the old behavior that maybe some parts of their code base are relying on. And hopefully it keeps performance for a lot of different use cases, right? Which is, again, because I have interest in pro-business for the standard, I can't really afford to shrug off different use cases or throw certain things out the window, because this needs to be everything for everyone. That's the point of being in the standard library. This kind of flexibility at this low level of design, I think, is very enriching and useful for the long run. So yeah, just some quick acknowledgments. I actually wanted to thank Aaron Ballman, who turned me on to actually going to the WG14 meeting in Ithaca, New York. And that kind of helped spark the fire in me to help fix the C standard, at least with relation to the encoding stuff. I can't fix everything. I also want to thank SBI, Robot, and Malak, and basically the general Lounge C++ community. There's actually a lot of them here in Germany and around Berlin. So I got to meet a lot of them, and they helped me feel very welcome. And I got to go out and get drinks and all other cool stuff. And I think that was the very first time I actually got like really drunk. Thankfully, I was able to make it home though, so not too worried there. It's good. I also wanted to thank Include C++ for being an amazing community. They actually have a very large presence here, and if you haven't seen anyone from there, you must have not been attending the conference. But if you really haven't, find some people. Guy Davidson, he works with Include C++. He's here. There's a bunch of other people here who also work with Include C++. They do a lot of diversity outreach. They do a lot of work in making sure that not only that everybody kind of feels welcome and included, and have a very nice atmosphere. And of course, this is a link. The actual website is includecpp.org, and so you can go there, and they have a Discord server and a bunch of other resources and stuff, and code of conduct and other things that will help you kind of be a better community member in general. Yeah. And so thank you very much. If you want to help make this text proposal a reality for the C++ standard, you can support me if you want to. There's a bunch of links here, and there's a bunch of this is actually a way too detailed list of everything I'm going to do, and the goals and the different breakdowns of what it is and everything else. So you can check that out if you want to. Now, of course, there's also my Twitter and my LinkedIn. My LinkedIn is actually / the PhD. I'm so happy I got that. For Twitter, I had to settle for the Phantom Derp, but don't tell anyone that's actually what the PhD means. I'm totally a doctor. Don't worry. And this is that's it. So thank you all for coming. Thank you all for listening to the talk. And any questions? Yes.
So, very interesting talk, and I'm really happy that you're doing this. That somebody's doing it. My question would be, I'm not sure that I see a lot of value in type erasing encoding in general. Even if you get runtime, you can encode it once. But even if there is, type erasing on one character, on one code unit, seems like you're going to have a lot of overhead for type erasure.
Yes. So this is actually something that I did notice. Of course I noticed it because I benchmarked it and I was like, wow, this is terrible. But I did actually notice it, and so there are hooks to allow an encoding to hijack the general high-level bulk conversion mechanism. So basically, you define. If we just backpedal for a second, I could probably show you. I gotta miss it. Okay. So we have the encode 1 and decode 1 functions here, right? The other thing you can do on encoding objects is you can define a function called encode and a function called decode, not without the 1 suffix. And what that means is that it will allow the implementation to hijack the bulk transcoding functions that I mentioned in my first talk. I give a whole talk about ADL extension points and a bunch of other stuff. But basically, and this is actually one of the encodings that I didn't show it here because again it gets into more complicated stuff. But you can define an encode and a decode function. It takes all the same parameters that will hijack the bulk transcode function. And so what that means is that basically what I do is I hijack the function and then I unravel the actual real encoding that we have, and then I call bulk transcode with the real encoding, right? So I'm not doing it once per character. I'm doing it once for the entire sequence, right?
Yeah, I've seen your previous talk, but like, is the bulk conversion, is it operating on the array of code points? So you convert code units to code points, or you convert between two different code units?
So I spent a lot of time talking about this in my first talk, but basically the way the API works is that at a general high level, I can only do one, and I can only decode one, have a code point, and then take that code point and then encode it. So I'm doing it one at a time through the entire thing, right? And the reason I do this is that it saves on memory, and it's also scalable, right? So you can write a encoding GB 108030, right? And you can plug it into the whole system, and the whole system will work. It won't be fast, but the whole system will work, right? And it will work arbitrarily with all other encodings because you have that bridge at the code point level, right? But that's slow, right? We all know that's slow. So this is where the fast transcode functions come in. And what happens is you write basically ADL-free functions that hook into the implementation and say, oh, I know you're converting between UTF-8 and UTF-16. I know the fast pass between that. Oh, you're converting between UTF-8 and UTF-32. I don't really have to do a decode step and then an encode step. I just have to do a decode step, right? And so it does all this stuff for you, right? In the background, right? And you yourself can opt into those, opt into taking control of that by writing those free functions. But that's all kind of discussed in the first talk. But yeah, no, it's very much the generic algorithm does do the one by one, like encode one, decode one, encode one, decode one, like slowly, right? But the typical high-level API that most users are using are the bulk conversion one, and the bulk conversion ones will always pick the fast path if it's available, right? Like, for example, I can't expect somebody to encode ISO 2022 Chinese to EBCDIC, right? Like those are two-way disparate encodings. There's no way that there's like a fast path between those two, right? So we use the generic algorithm as a way of being able to allow you to go from that to that, right? And that's the way. That's why that bridge is there. But for known encodings like UTF-16, UTF-32, like all that stuff, we definitely provide fast paths, right? In fact, that's actually why ASCII is one of the encodings included in the standard, because there's a lot of ASCII data out there, and we know that we can fast path that to like all the other encodings, right? So that's why that exists. Yeah. Does that answer your question? I kind of went on for a while there.
Part there, like, so the way, for example, as far as I remember, Chromium does this. It would go from code points to the array from the code units to the array of code points. And then from the array of code points, then you get all your flexibility that you want. But you get an extra allocation of the array of code points, but you get the flexibility. And you can still do the bulk operation. Yeah,
so the only reason I wanted to avoid doing that is that that would require me to basically allocate the thing up front, right? And that's a memory penalty, right? And so again, I want this also to work on small devices, and so that's why I kind of made the design decision I did. But there's nothing that stops the user from doing an explicit like bulk encode or a bulk decode to get to all the code points, and then doing a bulk encode from there to get like strictly to all the things. And you can do that separately. I mean, I think at some point I might provide a function to do that for users, like an eager, something called like eager transcode that does that kind of work for you. But right now I just wanted the most generic thing that works with like the